Hello, today we're continuing with our GCSE Physics Revision series looking at logic gates. In the video on rectifiers and capacitors, I introduced you to the idea of a rectifier, and I said that it was made up of two materials, N-type and P-type material. Now let's just remind you what they are. They are both made of silicon. Silicon is a semiconductor, which means that it does have some free electrons, but nowhere near as many as a conductor, a metal, has. But neither is it an insulator, but you won't get very much of a current flowing through a semiconductor because it's halfway between a conductor and an insulator. But what you can do with silicon is to dope it. And what we mean by that is that one atom in every million, approximately, is replaced by a different atom. And there are essentially two ways of doing this. In one form, you take the atom and you replace it by an atom of phosphorus. Now the point about phosphorus is that compared with silicon, it has one extra electron. So if you've got one atom of silicon per million being replaced by a phosphorus atom, then you will have slightly more electrons than you would have had if you hadn't doped the material. So there's a net negative charge, and we call that N-type, meaning negative, N for negative. Or you can dope the material with something like aluminium or boron. The point about these is they have one fewer electron in the outer shell than silicon does. So there is, as it were, a deficit of electrons in this material compared with what it would have been if you hadn't doped it. And therefore it has a net, as it were, positive flavour because it's not as, it's got a deficit of negative charge. So you could say that's a positive charge. So you've got N-type and P-type material, which are both silicon but doped with different materials. And then I said you just bring them together so they physically touch one another. And when you do that, I said you get what's called a depletion layer between the two. Because what effectively happens is that the, as it were, net surplus of electrons balances the net deficit of electrons where they touch, to produce a depletion layer where there is effectively no free electrons. And then I said if you take this material, this NP material, and you try to pass a current through it, and don't forget this is the depletion layer here, if you try and pass a current through it, it depends which way you try to pass the current. If you put the battery such that you've got the positive side on this side and the negative side on this side, I said you've got no problem that the electrons, the free electrons, both from the battery and in the N-type material, will happily travel across the depletion layer and the P-type because they are going towards the positive charge. Negative charged electrons will be attracted to the positive side of the battery. But I said, if you do it the other way round, such that the electrons are now going to try and flow to the positive charge here, well, these free electrons will flow, but you haven't got any free electrons either in the depletion layer or in the P-type material. And so actually in this direction, no current will flow. And that is the essence of a diode. The current will only flow in the N to P direction. And that's what we covered with rectifiers. But now I want to take the story on a little bit further, because now I'm going to have a substance which consists of N and P and N. And I'm going to ask what happens if you put a battery across that, essentially. Well, remember the whole point about the diode was that you can get a flow from N to P but not from P to N. So here you can get a flow from N to P but not from P to N. So since you want the current to flow in this direction, in other words, you want the electrons, rather. The electrons are going to flow towards the positive charge. They will flow from N to P, fine, but they won't flow from P to N. So that's not going to work. Nothing will flow. What happens if you put the battery the other way round? Now the electrons will want to flow to the positive charge. So fine, they'll go from N to P, but they won't go from P to N. So if you want to try and get the current to go that way, that's not going to work either. So now we've built a device which doesn't let the current flow either way. And you might say, fat lot of good that is. But this is where it gets clever. You take your NPN material, which of course, as we've just shown, will not allow a current to flow either way, and you introduce a very, very small current into the P-type material. That is to say, you are providing a few electrons. And what you find, and there's quantum mechanical reasons for this that we don't need to go into, but essentially you can, I think, get the flavour of the idea that if you're introducing some free electrons into here by putting a small current into here, then that will mean that the obstruction, the fact that there were no free electrons to flow, is no longer the case, and now a current will indeed flow, or we'll now talk about conventional current. Obviously electrons are going to go in the other direction, so we're going to have the plus here and the minus here. The conventional current will flow plus to minus, the electrons will flow minus to plus. So we're now talking conventional current. Conventional current will now flow. A small current into this bit will result in a large current flowing across the main device. So we've essentially invented a switch. If you don't put a small current in here, no current will flow across the device. If you do put a small current in here, then you will get a larger current flowing across the device. So whether or not you put a current through here will determine whether the current here flows. That's a switch. And it is also called a transistor. This end of the transistor is called the collector. This end of the transistor is called the emitter, and this end is called the base. And the conventional current flows from the collector to the emitter, provided there is a small current coming in through the base. If there is no current coming in through the base, then there will be no current travelling between the collector and the emitter. And this is particularly called an NPN type transistor. And just so you know, the current out of the emitter will equal the current in to the collector plus the very small current that comes in through the base. Now that is always a small current, so in practical terms the current coming out of the emitter is of the same order of the current that goes into the collector, because this current is going to be very small. And the symbol for electronic circuits for a transistor looks something like this, where this is the collector, this is the emitter, and this is the base. So essentially, provided a small current is coming into the base, it means that a conventional current will flow from the collector to the emitter and out the other side. But if no current flows into the base, then no current here will flow. Consequently, this is essentially a switch. So how is that going to help? Well, here I've drawn a circuit diagram, and I'll give you an example of how it helps. Well, it's quite simple. We've got a 9-volt battery. In this arm, we've got, you may recognise this, we saw this when we did potential dividers. We've simply got two resistors. A fixed resistor, R1, but here we've got a thermistor. Now just remember, the point about a thermistor is that as the temperature increases, the resistance decreases. So when the temperature is high, the resistance is low. When the temperature is low, the resistance is high. So this will vary its resistance as the temperature changes. Here we've got a very large resistance. Why? Because I said we only need a small current going in through the base. So a large resistance makes sure that you don't have too big a current going into the base. Down this arm we've got a light emitting diode, so that light will come on provided a current flows down this arm. And here we've got just a transistor. And remember, that transistor is, to all intents and purposes, a switch. If there is a current coming in through the base, then the switch will be closed and essentially current will flow down this arm, which means the light will come on. But if no current goes through the base, then the switch will be open, so nothing will flow down here. So now let's think about it. When the temperature is high, the resistance will be low. So the resistance will fall to almost zero. Consequently, the current that's flowing this way has a choice of either going through a very high resistance or going through a very, very low resistance. It chooses to go through the low resistance. So virtually no current at all goes through this way. To all intents and purposes, there is no current through the base. Consequently, the transistor as a switch is open, and no current will flow through here. So the light doesn't come on. Now what happens if the temperature drops? If the temperature falls, the resistance increases and you get quite a large resistance here. And now when the current is coming down here, it can go through this large resistance or it can go through this large resistance. And the answer is it will go through a bit of both. So you do at least get some current flowing through this large resistance. And therefore there will be a current in the base, and therefore the transistor as a switch will be closed, and therefore a current flows down this arm, and therefore the light emitting diode lights up. So when the temperature was high, the resistance was low, you got no light. But when the temperature was low and the resistance was high, the light came on. So this is a device which uses the transistor as a switch, such that if the temperature falls below a certain value, the light comes on. So this is potentially a means of operating a thermostat to turn the heating on when the temperature falls below a certain level. And the transistor participated in the logical decision of whether or not to turn on the heating. And transistors are, or at least were, at the heart of logic circuits. These days they're designed in a different way, but for our purposes we're learning how they used to work, using individual transistors in a combination in order to provide logical outputs. And the typical way in which it used to work is that you would have the base input coming through obviously a large resistor so that you always got a small current, which is what's required. And that would come into the transistor, whose circuit looks like this. Remember, this is the collector, this is the emitter, this is the base. And basically what you arrange is that there either is a current coming through or there isn't. Or typically there is a voltage on that line or there isn't. If there is a voltage, that will make a current flow. If there isn't a voltage, there won't. What that voltage is depends on the particular circuit you're in, but 5 volts is not uncommon. So you would arrange that either there is a 5 volt potential on this line or there's a 0 volt potential on this line. If there's 5 volt, a current will flow. If there's 0 volts, no current will flow. And if a current flows, the switch is the switch is closed, meaning that a current can flow from the collector to the emitter. If there's no volts, no current flows in through the base, and that means there can be no current flowing between the collector and the emitter. And it's that essential diagram that works for logic circuits. Let me give you a circuit diagram for what's called an AND gate. Now, first of all, I'll just draw you what the circuit symbol is for an AND gate. It looks something like this. And it has 2 inputs and 1 output. And essentially what you're saying is that the input can either be 5 volts or 0 volts, and the input here can be 5 volts or 0 volts. And what we want to say is we only want an output, which is usually itself 5 volts. We only want an output if both of the inputs have got 5 volts coming in. If one but not the other, or neither, we don't want an output. So it's called an AND gate. You only get an output if the first and the second have got 5 volts attached to them. So how would you do that using the transistor I just designed? Well, you take the first transistor, which has got the large resistance going into the base, and there's the actual transistor itself, there's the collector, there's the emitter, and then you have another transistor here. All these things are designed with multiple transistors. So essentially we've just got, I'll just push that up, we've essentially got two transistors, each with of course a high resistance, so that the current coming into the base is going to be low. And what do we say? We say that if there is a current coming in here, in other words, if that is 5 volts, so that there's a current coming in here, and if there is 5 volts here, such that there is a current coming in here, both of those transistors will be closed and a current will flow through both the transistors. Essentially, the current will therefore flow continually along this line. But if either of these, let's say this one is 0 volts, then there won't be any current coming through the base, and therefore this transistor will be closed. And even if this one is open, you're still not going to get any current flowing through. And similarly, the other way round. If this were 5 volts such that this was open, but this was 0 volts such that this was closed, you're not going to get any current coming through. You've got an AND gate. You only get the current flow if both of the inputs have got the 5 volts on them. If both or either have got 0 volts, no current is going to flow. That is an AND gate. Now, I'm not going to show you how you use transistors to build other types of gates because you don't need to do that. But if you're interested, you can see my video on an introduction to logic gates, which is in the A-level revision playlist, and that will give you more details. But I'm just going to continue with the essence of what you need to know. We've already described the AND gate, which you'll remember has the symbol like this. And in principle what it means is that you only get an output if both the inputs have got a voltage on them. So that's the so-called AND gate. There's another gate which has a different shape, and that's called the NOT gate. The NOT gate. And what that does is it says if you've got a positive voltage of say 5 volts on the input, you get no output. If you have no input, you do get an output. And these are, the way we represent this is through what's called truth tables. So I'll just draw you a truth table for the AND gate. We'll call the inputs A and B, and we'll call the output OP, that's the output. And what we do is when we represent the inputs and the outputs, if there is a positive voltage on the input or output, we assign that the number 1, and if there is no input or output, we assign that the number 0. So in other words, what we're saying is if A and B have got positive voltages, so that's represented by the number 1, we want the output to have a positive voltage, so that's a 1. But if A has a positive voltage but B doesn't, we want the output to be no voltage. Or vice versa, we still want that to be no output. Or if neither of the inputs has a voltage, we want no output voltage. So remember, the number 1 represents that there is a positive voltage, say 5 volts, and the number 0 means there is no voltage on it. So in other words, the AND gate works. This is what's called a truth table. So this is the truth table for the AND gate. In the AND gate, you only get an output if both the inputs have got a positive voltage on them. Otherwise, you get no output. The NOT gate is slightly different because you've only got one input and one output. And what you want is that if there is a positive voltage on the input, you want no voltage on the output. And if there is no voltage on the input, you want a positive voltage on the output. So in other words, it reverses the position. Whatever you put input, you get the opposite in the output. That's a NOT gate. And then we'll do one more. It's called the OR gate. An OR gate looks a bit like an AND gate, but it has a kind of crescent rather than a straight line, which is what you would get in the AND gate, remember? So the OR gate has 2 inputs and 1 output, and the truth tables, we'll call these inputs A and B. So the truth table for an OR gate is that if one of them has an output, an input, then you get an output. In other words, if one or the other, so even if it's 0, 1, you get an output. Or indeed, if both, you get an output. But if neither, then you don't get an output. So if A or B, or both, have got a positive input, you get a positive output, right? So here A has got a positive input, but B hasn't. Here A hasn't, but B has. Here they both have. And in all 3 cases, you get an output. A or B or both, hence OR gate. But if neither, if A and B do not have a positive input, you don't get a positive output. That's called an OR gate. And you can get the reverse of all these things. You can have what's called a NAND gate, which means a not AND gate. And it looks a bit like the AND, except you put a little circle here, and that makes it a NAND gate. And the idea here is that it's precisely the opposite of an AND gate. So if you get positive inputs on both channels, you get nothing on the output. It's NAND, it's not AND. On the other hand, if you get a positive input on one but not the other, you do get an output. And indeed, if you have no inputs on either, you do get an output. A NAND gate means you get an output for everything except where it is an AND. It's a not AND gate. And you can have a NOR gate, which is rather like the OR gate, which needs, of course, the crescent. And to show that it's a NOR gate, we put the little circle on it. Once again, you're going to have 2 inputs, call them A and B, and 1 output. Here's A, B, and the output. And the thing about a NOR gate is that if neither of them have got an input, you do get an output. But if any other situation applies, you don't. So provided neither A nor B have got an input, which is this, you do get an output. But if either of them have got an input, or both of them have got an input, you don't get an output. Which is all fascinating stuff, but how are we actually going to use this practically? Well, I'm going to show you a design for a warning system. I want to be alerted if I've switched the equipment on and it gets too hot, or a door is open and it's at night. So this might be a warning system for my house. I switch the warning system on. I want to know if the house catches fire, which means it will get hot. I want to know if someone breaks in, which means the door opens. And I only want to know this if it's at night time. I've perhaps got other arrangements during the day. So the system must be on, it must be night, and I want to know if it gets too hot or if the door opens. How can I use the logic circuits that we've just designed to tell me? Well, obviously I'm going to need 4 gadgets which will tell me if the things that I want to check are in one state or another. So I'm going to have some device on the door which is going to emit a positive voltage if the door is closed, but no voltage if the door is open. For example, a simple contact. Once the door is open, the contact is broken. There is now no current flowing, no voltage. So in other words, there will be a positive voltage if the door is closed, but no voltage if the door is open. I need a heat sensor. That heat sensor might send out a positive voltage if it's hot, but no voltage at all if it's cold. I need a light sensor to tell me whether it's night or day. That sensor sends out a positive voltage if it's light, no voltage if it's dark. And obviously I'm going to switch on the equipment in the first place, so I get a positive voltage if it's on, but I get no voltage if it's off. So these are my main inputs. How am I going to fit them into a logic circuit? Well, firstly, I obviously want to have a positive voltage if the things that I'm worried about happen. At the moment, I'm getting a positive voltage if the door is closed, but I don't care if the door is closed. I want to know if it's open. So I'm going to put a NOT gate here, because then if the door is closed, that means I will get no voltage out of the NOT gate. But if the door is open, which of course ordinarily means there's no voltage, I want the opposite. So I want a positive voltage coming out when the door is open, because that's what I'm worried about. Here, I'm okay because I want to know when it's hot. And when it's hot, I'm going to get a positive voltage. I want to know when it's dark, not when it's light. At the moment, I'm getting a positive voltage when it's light. That doesn't interest me. So I'm going to put this through a NOT gate. So if it's light, the NOT gate will give me no voltage. But if it's dark, which is what I do want to know, it will give me a positive voltage. Here I'm fine. I only want to know when the switch is on, and when the switch is on, I get a positive voltage. When it's off, I get nothing. So now I've got a situation where I'm going to get positive voltages for each of these when the circumstances I'm interested in arise. In other words, when the door's open, when it's hot, when it's dark, and when I've switched on. Now I'm going to put these top two through an OR gate, because I want to know if the door is open or it's caught fire, or both, of course. So I will get an output from an OR gate if either the door is open or the house catches fire, which is what I want. And if they both happen, I'll still get an output. I don't want an output if the door is closed and if it's cold. So I only want an output if either the door's open or it gets hot. Down here, however, I've put them through an AND gate, because here I want the situation where the switch is on and it is dark outside. It's not a case of OR. The conditions are the equipment must be on and it is dark outside. So now we go through a AND gate. We will only get an output if it is both dark and the equipment is switched on. And then finally, I'm going to put the outputs of these two into another AND gate. And the output of that will go to a light emitting diode, which will come on. So in other words, this will only be positive if either the door is open or the house catches fire. And this will only be positive if it is both dark and the equipment is switched on. So I'm only going to get a positive output here if the equipment is switched on and it is dark outside, and either the door is open or the house catches fire. And that's precisely what I want to know. And in those circumstances only, there will be an output here which switches on the light emitting diode, or if you like, switches on an alarm. So that's quite a complicated example, but I hope it shows you how you use these different types of gates, each of which is made up with the use of the transistors that I showed you to make logical decisions that cause something to happen if and only if a certain set of circumstances apply. Finally, I just want to tell you about a related piece of equipment called a relay. Now, the point about relays is that you might have a circuit in which there is transistors, and you might have a circuit with the output, the consequences of what the logic determines, and that might have a motor in it. And the point is that for circuits that have transistors in it, you're usually talking about fairly low voltages, 5 volts, very small currents. Whereas if you've got a circuit with a motor in it, you may be talking about 250 volts and a high current. And you don't want those two circuits to mix, because if you put very high voltages through transistors, you just simply blow them up. So you've got to keep those two circuits separate. And yet the output of this circuit has got to influence this circuit. This circuit has got to determine whether to switch the motor on or off. How are you going to do that if you can't put the two circuits together? And the answer is you use a relay. So firstly, here is the output from my logic circuit. I'm not going to redraw it, we did that last time. So we're going to assume that there's going to be an output which is only positive if all of those warning signs materialise. And what you do with this output, instead of taking it to the light emitting diode as you did before, you actually take it to what's called a solenoid. Now we did do this when we did electromagnetism. A solenoid is just simply a sort of a bar of iron round which you wrap your coil of wire like this. And the idea is, of course, that when a current flows, this will create an electromagnet. So there'll be an electromagnet and a magnetic field created within the iron bar. But if there is no current in this circuit, then there will be no magnetic field. And so the consequences is that when you've got all the conditions of your logic circuit are satisfied, a current flows and that turns this into a magnet. Now what you then do, I've not left myself much room, so I'm going to redraw the magnet down here. Here's the magnet with the coil around it linked to the logic circuit. What you do is you have a pivoting arm made of insulating material. But at the end of here you have a piece of metal, and at the end of here you have a piece of metal. But this is insulated, remember, so no current will flow in this piece of material here, only metal at the end. What will happen if this becomes a magnet? That magnet will attract that metal, and the metal will swing down on this pivot to touch the magnet, which means that this end will swivel up. If this end swivels down, this end swivels up. Now suppose I've got a piece of metal here linked to, oh, I've gone a bit too high, linked to the circuit in which the motor is, like that. What will happen is the motor, ignore that bit there, the motor will only come on when those two join. In other words, when there is a complete contact between the two. So ordinarily, there'll probably be a spring on this to make it sit nicely like this. So ordinarily the contact is open, consequently no current flows, consequently the motor doesn't come on. But when the logic circuit is satisfied such that all the conditions that we set out before are satisfied and you get an output, the output will cause the solenoid to become a magnet. The magnet causes this part of the arm to swing down because the magnet attracts the piece of metal. That in turn causes this part of the arm to swing up, and now the two contacts meet, and this now is a complete circuit and the motor comes on. But notice that electrically the two circuits are entirely separate, and they're kept separate by this bar, which is insulating material, so no current can flow between the two. And that is called a relay.